Hello, hello. What's going on, guys? Whoa. This is brand new territory, okay? Hold on. I need to add a filter onto this. Filters, add compressor, I guess. We can just do that and then add a limiter, and then let's increase the threshold. Yes, guys, yes. Increase the threat. Hello. Output gain. Hello. Yes, I'm talking. Hello. I'm talking. I'm talking quieter, and I'm talking louder. Hello. Sorry, guys, I'm trying to figure this out. Hold on. I need to listen to myself now. Hello. Sorry, guys, I'm trying to figure this out. Hold on. I'm talking. Hello. Maybe having a compressor on is not the best idea, because then you can hear like all of it rubbing against my my clothes. I think just the limiter is okay. The limiter, is that okay? And put gain on it. Yeah, we'll just do gain. A limiter and gain is what we'll do. Hello. Gain of 2, gain of 6. Hello. I'm increasing the gain a lot. Okay, this should be okay now. Hello. Should be able to hear me. Oh, hello. I'm increasing the gain a lot. Okay, this should be okay now. Hello. Gain of 2. Still kind of like gain of 6. Hello. I'm increasing the gain a lot. On my clothes. Gain of 2. Still kind of like gain of 6. Hello. I'm increasing the gain a lot. On my clothes. Gain of 2. Still kind of like gain. Okay, whatever though. You guys are gonna have to deal with the worst quality. I don't really care. Only reason why I want this in and not the actual microphone right now is because I don't feel like using it. Okay, that's why. I don't feel like using it. Also, what's going on with the webcam? It's pretty bright. What's going on with my filters? Yeah, we can just leave the filters off. All right. So, 2 things. 1, you might have noticed, we're using this today. Okay. 2, also, this is not just a crop. Okay, the monitor is 4:3. I put it in 4:3 ratio just because I think, I don't know. I don't know why. I'm gonna switch it back probably when I'm like actually doing stuff. But like 4:3 ratio, it just seems like the way to go. You know what I mean? Let's turn this on, kind of low volume. Not very low. I think that's better. Okay, I don't have any filters on this. Okay, so you guys are hearing what I'm hearing, presumably. Sorry, also my throat is just fucked up. Close the window. So how are you legends doing? It's been a while since we've actually since I've done one of these. I'm so sorry, hold on. I don't know why my throat is like not great right now. I might need to just hydrate more. Do I need to hydrate more, or do I just need to talk? I haven't talked at all today, pretty much, actually. What?
I'm gonna go first. Wait. We should have a proper start to each session. You know what I'm saying?
Yeah, we all go.
We should have a way to segue. You have a way to segue into the purpose of whatever this is we got going on. So, what should we say?
Well, you're the one who brought it up, genius.
Shoots. Hey guys, what's going?
Punishment. Sorry, I'm just seeing our video has 14 views. What the hell? That's a lot. Your face after that's actually just like leveled up. Dude, that's so much better. Oh my god. That's actually just like level.
I changed my mind. Let me think. Hold on. Ooh, okay.
Yeah, you know what? That video was good. It was good. It's better. How loud is the capture in comparison to what you guys are actually hearing? I also haven't like edited anything about this actually. So is what you guys are actually open up. Let me open this up. Sorry, also when I'm like clearing my throat, it probably sounds horrible for you guys. It probably sounds horrible. Yeah, it is actually louder than what I think it should be. So we'll decrease this. Yeah, it is actually louder. Oh, shoot. Than what. I'll decrease it by like 5. Now it should be at a level I think it. That is comparable, but I do need to pause this. I'll decrease it by like 5. Now it's just not. That is comparable, but I do need to pause this. A little too low. Okay, so like 4 is good, but it still looks too loud. I don't know, dude. I don't know. Is that too loud when I talk like this? But it still looks too loud. I don't know, dude. I don't know. Is that too loud when I talk like this? But it still. Okay, that's not too loud. Okay, whatever. Whatever, dude. Listen. Too loud. Okay, whatever. I was gonna say a bad word, but frick you if you're getting all twisted up over this stream. You know what? Who cares? Let's edit. What's our tags? Math, study, real analysis, fun, study with me, chill, vibe, epic. Those are our tags, guys. Those are the 10 tags you need to add to your videos in order to be a god. The people that are above me are moving out or some shit, and they're like fucking banging everything all around, and it's so goddamn annoying. Oh my god. Oh, you know what'd be dope if I could change the aspect ratio of the. What the hell is vivid pixel? It just kind of makes it like weirdly sharp. What is ASCR? I don't know what any of these are. If I could change the aspect ratio of the monitor on the fly, that would be dope. Because I don't have to go into my settings and then like change it. But honestly, it's not too complicated to go into the settings and change it. But, you know, it would just be cooler if I could just, boom. What would be even cooler? I'm so sorry, guys. I don't know what the hell it, like I have like something stuck in my throat. Sinuses today are just acting up. I don't know why. But what would be even cooler is if I, for example, the earbuds are constantly spiking, so I should probably turn down the gain to like 1.7. I think that enough gain is fine. That is fine. Maybe even just to like 0.6. A little bit of gain, that's fine. I can increase it a little bit more. Let's just do 1.10. 1.10 gain, that's pretty good. And then we have the limiter on it. Okay, wait, what's the threshold on the limiter? It's 0. Let's decrease it by like 1.6 is the threshold, and then negative 2.6 is the threshold, and then, okay. Should be okay. Should be okay. Okay. Anyways, what was I talking about? What was I talking about? Something about them moving out upstairs. Fuck, what was I talking about? I can go back instead of having to remember. What was I talking about? Okay, I can increase a little in. Sinuses are there, just I don't know what the hell it, like I have like something stuck in my throat. What would be even cooler is if I, for example, what would be even cooler is if I just had a 4x3 monitor. Guys, you ever, listen, 4x3, let me tell you, 4x3 is the aspect ratio, man. It's just great for like, I don't know, doing work. Like it's just, everything's kind of like in your field of view. Like 16:9, when things are like when your monitor is big enough, when your things are like for a laptop screen is perfectly fine. Like I think for MacBook, guys, I don't know what's going on. Oh my God. But anyway, for a MacBook, right, the aspect ratio is 16:10. But like the screen is small. Like I have a 14-inch. And so like the screen, it's like, especially if you're further away from it, you can see everything. But like when you get like I think this monitor is 24 inches or something like that. When you get like a 20 plus inch monitor, 16:9, some things are just like out of your like view. But with 4x3, you can make it a lot bigger and everything is still in your view, you know? Like nothing's outside of the zones of like, I can't really read this. That's one plus in terms of 4x3. Another plus in terms of 4x3 is just like, I don't know, it just, it feels more akin to like doing work. That's probably just my bias and like growing up using 4x3 monitors, like in school and at home, just doing like things that were, I don't know, no, because I grew up using CRT TVs to play video games, and those are 4x3. So I don't know, but yeah. Dude, playing Skyrim on PS3 on a CRT TV was so sad. Because in the top left, the text was cropped for a 16:9. So when you were playing, if it said like there are enemies you can't fast travel, I would just see the like you can't fast travel part, and I wouldn't see that there are enemies nearby. So I'd be like, why can't I just fast travel? And I would be so annoyed. And that was like so sad until it wasn't until the PS4 came out that I actually got an HD TV. Like an HDMI input, because PS4 didn't have AV input anymore. It only had HDMI. So that kind of changed the world. Dude, PS4, and then I remember playing the PS3 and then playing like GTA 5 on the PS3 on the 16:9 monitor. That was crazy. What did I get the PS4 for? What was I playing? I was playing Infamous Second Son, definitely. In the early days, what was I playing? Because it's not backwards compatible with the PS3, so I don't know. I was still playing Black Ops 2, definitely. But yeah. Yeah, man, so I don't know, I'm just maybe this is just a phase that I'm going through, okay? But it probably is just a dumb, stupid phase. Because not only am I going back to 4x3, I'm also going back to paper, using fucking paper to do my work, just because it's so much more like, it's just less hassle. There's less barriers between you and writing down your ideas. Even like, oh, I ran out of space, boom. That's so much less hassle than like swiping up and like making sure, like, I don't know. I think like tablets are cool, but they're not at the point yet where they can replace the good old pen and paper. I think they're just very useful though. Like I use it to like, do my homework on it, and then like you can not only can you like do your homework and like export as a PDF, you can include screenshots of like the question that they're asking you. But yeah, like it's so convenient for like doing assignments, but it's just not conducive. At least for me, not only have I tried like the traditional notes method, like, imitating how notes are, like paper notes with like the page flip turn and everything. But I also tried infinite canvas, like mind mapping, so that like that, which is something that's only unique. Like you can only use an iPad to like mind map stuff, draw like large like bubbles and everything like that kind of connect on an infinite canvas. But neither of them, they just weren't working out. Like iPad is just good. It's good for like, I don't know, if you're just trying to do like temporary stuff. I don't even know. I'll look at those later. But iPads are just good for not temporary stuff. What am I talking about? If you need to do like notes that also require like adding in links and stuff like that, that's what iPad is really good for. What's this reminder that I got? I did that. I saw this thing on eBay for a humidifier, and like I was trying to find filters for my humidifier that I can buy, but the filters were like, $15, $20, $25, that kind of range, depending on the amount of filters that came with it. But I saw like a new humidifier that didn't require a filter was just $16. So I was like, I'm just gonna get a new humidifier. Obviously, it's probably gonna be it's like open box, and it's probably gonna be used and like filthy. You can just clean it. And also, like, I think this one has like the mist, so it shows the mist when you're using it. And I think that'll just mentally make me less dry and more humid, just because I can see like the water vapor in the air. I don't know what it is. It's totally just all in my head. But it would also just be nice to like not have to buy new filters all the time, because the air in my place is pretty dirty. So the filter gets dirty pretty quickly. And no offense, but the humidifier is not gonna clean the air enough to like be of safe breathing quality. Like it's not a HEPA air filter. It's just a filter for like contaminants. That's pretty much it. So anyway, with all that being said, let's get into the meat and potatoes. But before that, guys, we're going to fill up on some more water. I've been trying to do more electrolyte. Yeah, these are lines that I added today. I've been trying to get in my electrolytes. So what that means is that I'm pouring this right above my iPad. If it wets it, it was meant to be. Destiny. I started putting like limes, or ideally lemons, but limes were cheaper in the store. Limes inside of my water, so I can get a little bit of extra electrolytes and stuff like that, and a little bit of salt as well. Trying to get more hydrated, without having to buy the electrolyte packets. Basically, I'm trying to become more healthy, more holistic as a person, and so one of those ways is by just making sure my health is in check. And so you got to be hydrated, but properly hydrated, I think the tap water here probably does enough. My Brita filter is like dead as well. Like I need to change the filter, but I'm not going to buy a new filter because that's more money this month than my budget is going to allow. So I'm just still using this old filter in hopes that it actually does something. But yeah, gotta be healthy in other ways. Oh, also because I'm sitting down. I did squats yesterday, so my legs are like stiff and tightening up. I'm getting that DOMS, delayed onset muscle soreness. But tomorrow I should go into the gym. I shouldn't do legs. I don't know what I should do tomorrow because my wrist is still kind of in pain, but I can probably, I don't want to push it. I don't want to do like bicep curls or super hard or whatever. So I don't know. What should I do? Probably just cardio and then shoulder and wrist stuff. I'll probably do that. Yeah, I still want to, but yeah, I should do like actual wrist warm-up stuff. So far, I've just been letting my wrist kind of recover. I haven't been doing much other than that. I should do like actual wrist weighted exercises to really get it going. But anyway, guys, the real meat and potatoes, why I know the reason why you're here, okay, and the reason why you're here is because, did I add that? Yeah, I did, pretty sure. Is hold up. I'm checking my mail. Okay, I'm not checking social media. That's one thing I wish I can do. I wish I could just totally... I wish I could have all the good parts about having an iPhone, but just translate it into a different medium. Like a smaller phone that kind of does less things and looks better. This camera design on the iPhone is so ugly. It's just like, look at this. This is horrendously ugly. Like, this is just ugly. Even without the case. The case is just nothing. The case just, you know, it's just a solid black color. Horrendously ugly. In the front, like the dynamic island, the pill, whatever you want to call it, it looks decent. The front looks decent. It looks fine. But the form factor is just like, just make it like slightly smaller. It's kind of just in an awkward zone right now where it's slightly too big and not small enough. Like, it's just slightly too big for my hands. Like, it can't reach into one of the corners normally. Why am I getting reminders? I already did this, please. Okay, but anyway, guys, the real reason why we're here is to read this. We gotta get through 2 derivatives. So we gotta read all of this. And I mostly understand most of this, so this should be more or less a breeze. But actually, we've never read... Oh, this is a new thing. We've never read our math textbook. We've just been reading solid-state physics. So, we're going to be reading math for the first time. I know, right, guys? It's incredible. So, zoom in a little bit here. There's just like an annoying sound. I think it's because they're vacuuming up. I'm just being distracted from all sorts of angles. It's too much. Too much distractions from everywhere. It's too much. But okay. Alright, guys. Functional limits. Consider a function f which maps from a domain A to the real numbers. Recall that a limit point C of A is a point with the property that every epsilon... This... a little bit too loud. Recall that a limit point C of A... Just had to brighten my monitor. Is a point with the property that every epsilon neighborhood... VE of C intersects A in some point other than C. A limit point C of A is a point with the property. Oh, you know what I should do? This is when it would be good to not have a 4x3. Hee 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 hee. Tee hee. You know what we can also just do though? Can we do this? This is just kind of dumb then. This is just kind of stupid. This is the smallest I can make it? No, I can make this smaller. I can make this one bigger. Okay, yeah, let's make this as small as it can go. This one, meet that. Okay. So if I have it correctly, oh, this is amazing. I also have the button on my mouse to undo. I thought that would be worthless, but it's not. Okay, so a limit point C of A, so we're talking about something A, and we're talking about a limit point C, that every epsilon neighborhood of C, where this is epsilon, every epsilon neighborhood VE of C intersects A in some point other than C. What? C is a limit point of A if and only if C is equal to the limit of some sequence, for some sequence that's inside of A, with that sequence not being equal to C. I don't get this. Recall that a limit point... Where's limit points again? Should be in closed sets, right? The definition of what a limit point is. A point X is a limit point of a set A if and only if X is equal to the limit AN for some sequence AN contained in A. I'm like hearing something move in my head. Phones. Not my head, my headphones, sorry. I don't know what it is. Anyways, I need an explanation on this. I want to refrain from using ChatGPT a lot because I've learned that it can just be wrong. Well, of course it can just be wrong, but like it can be pretty wrong. Explain intuitively this statement about the epsilon neighborhood definition of a limit point. And you're looking at a specific point C, which may or may not be within the set A. Oh, we're talking about its may or may not be. Oh, so let's come up with the example that C is out here, then an epsilon neighborhood does not intersect A. Oh, C just exists? The size of this neighborhood is determined by epsilon. If epsilon is smaller, your neighborhood is tighter around C. And if it's larger, the neighborhood is broader. A point C is considered a limit point of the set A if no matter how small you make this epsilon neighborhood around C, you always find points from A inside this neighborhood. This idea is closely related to the concept of a sequence converging to a limit. If you can find a sequence of different points in A that get closer and closer to C as you go further along the sequence, then C is the limit of that sequence. There's another way to say that C is a limit point of A. Even if C is a limit point of A, it doesn't mean C is actually in the set of A. It can be just outside, yet still be a point where members of A accumulate infinitely close to it. However, if set A includes all its limit points like it does in a closed set, then C would indeed be part of A. Yes. Because at this point, if we make, if we make A an open set and then we say that C is right here, then we can come up with some epsilon neighborhood that includes points of A. So C is a limit point of A, even though A does not include all of it. Clear. Boom. That's genius. Okay, this is good. Just had to refresh my memory. But yeah, it's with all these mathematical, logical definitions of like what these things are, like so stupid. It's not stupid. It's like literally the opposite of stupid. And I shouldn't use the word stupid. I need to stop using one word phrases that can catch everything. Everything is stupid. No, I need to be more specific with my language. It's so unintuitive and seemingly backwards sometimes. Boom. Okay, if C is a limit point of the domain F, then intuitively, the statement the limit as x approaches C of f of x is equal to L is intended to convey that the values of f of x get arbitrarily close to L as x is chosen closer and closer to C. The issue of what happens when x equals C is irrelevant from the point of view of functional limits. In fact, C need not even be in the domain of f. The issue of what happens when x equals C is irrelevant from the point of view of functional limits. So it's get arbitrarily close to L, okay? The structure of the definition of functional limits follows the challenge-response pattern established in the definition for the limit of a sequence. Recall that given a sequence AN, the assertion the limit AN equals L implies that for every epsilon neighborhood centered at L, there is a point in the sequence, call it AN, after which all of the terms AN fall in that epsilon neighborhood of L. Each epsilon neighborhood represents a particular challenge, and each N is a respective response. I don't really like this way of thinking about it. For functional limit statements, such as the limit as x approaches C of f of x equals L, the challenges are still made in the form of an arbitrary epsilon neighborhood around L, but the response this time is a delta neighborhood centered at C. So yeah, this is kind of how the function works. So you have some point. Is it going to like refer to the figure here? Yeah, okay, it does. Okay. So yeah, the limit as x approaches C of f of x is equal to L. This is kind of like saying C, where this is x. This is the output space, which is f of x. And so we have as x approaches C, so not even at C, but as x approaches C, then f of x, say this is a point L, so it'll approach that, or the f of x is going to be equal to L. This is the picture that we got going on. Listen. Okay. What I was gonna say is listen. Also, I need to start writing down like things that I can never mind. If I were to say it out loud, it would sound cringe. But anyway, listen, we're no longer dealing with just this one line and a bunch of, things like that. We're talking input and output space now. Okay, we're talking I/O space, all right? Okay. Dude, I need to get the Logitech unifying receiver so that this mouse can pull at like a much higher rate. And yes, dude, the MX Anywhere 3, such a goated mouse. I just wish every now and then the Bluetooth connection will hit 120 hertz polling, which like it feels so smooth. It's like, wow, it's so responsive. But that's not all the time. If this could hit 120 hertz poll over Bluetooth all the time, that would just be goated. but it can't consistently. It only can consistently if you use the unifying receiver. Or if you plug it in? I wonder, actually. Mouse polling rate checker. Let me actually see. Will it be better if I plug it in directly? Let's see. Okay. I don't doubt that it will. Or maybe I should doubt that it will. Okay, let's plug it in. Boom. Really? 90 hertz with it plugged in. You gotta be kidding me, dude. There's no way it's only 90 hertz when plugged in. That's crazy. Only 90 hertz? Are you serious? And then not plugged in? It's the same thing. I guess it doesn't communicate over wired, does it? No, it's only Bluetooth or the unifying receiver. That's so strange. Wow, so the plug is only for charging, not even communication. That sucks. That's actually really lame. That just docked it down a couple points. But yeah, it's only 90 hertz. Sometimes it hits 120 though, and it's really smooth, and it's like, whoa, that's crazy. Or 160, I forget what it was, but yeah. Anyways. Okay. Functional limit. Let f, blah, blah, blah. Let f be a function that maps from a domain A to a set of real numbers. And let c be a limit point of the domain A. We say that the limit as x approaches c of f of x equals L, provided that we say the limit as x approaches c of f of x equals L, provided that for all epsilon greater than 0, there exists a delta greater than 0, such that whenever x minus c is less than delta, and x is an element of A, it follows that f of x minus L is less than epsilon. Yeah. So whenever x minus c is less than delta, then you should have that f of x minus f of c is less than epsilon. And this is just f of c. You can call this L, whatever. But yeah, this basically means that as the distance between x and c gets arbitrarily small in some delta neighborhood, then you want the distance between L to be small as in an epsilon neighborhood. And this epsilon neighborhood, yeah, look at that. And this epsilon neighborhood is related to this delta. So you pick some sort of delta, like, I don't know, epsilon over 2 or something like that, you know? This is often referred to as the epsilon delta version of the definition for functional limits. Recall that the statement f of x minus L is less than epsilon is equivalent to f of x is an element of the var epsilon neighborhood of L. Yes, that's true, because this is that neighborhood of L. Likewise, the statement x minus c is less than delta is satisfied if and only if x is an element of this var delta neighborhood of c. Would you look at that? Wait, why is this not fully showing up on the screen? Oh my god, oh no. Oh, wait a minute, wait. Oh, so check that out. I can have my, actually, I didn't realize that. I can have my webcam a little bit uncropped then. So let's just increase the cropping a little bit. Wow, look at that. Boom. I'm a little bit wider. Okay, there we go. Gap is gone as well. Wow, would you look at that? Boom. Okay, so we can have our webcam like this. Yeah, I kind of like having a little bit of a wider webcam. But then we just have this black space below us, which is ideally where we would put the chat, but nobody's chatting. So we could do that though. Browser, we can do this as like chat. If you can like pop out chat, I don't know. Do 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 do. Dum 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 dum. Do 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 do. Do do dum. Bro, remember Brawl Smash theme? That's so good. Anyways, the additional restriction at 0 is less than x minus c is just an economical way of saying x does not equal c. I guess so. Recasting definition 4.2.1 in terms of neighborhoods, just as we did for the definition of convergence of subsequence, amounts to little more than a change of notation, but it does help emphasize the geometrical nature of what is happening. Okay, functional limit topological version. Let C be a limit point of the domain of f. We say the limit of x approaching c of f of x equals L, provided that for every epsilon neighborhood VEL of L, there exists a delta neighborhood var delta c around c with the property that for all x, which is an element of this, different from c, with x blah blah blah, it follows that, yeah, this is just restating this except using these terms. And remember, this is output space and that's input space, so then yeah, so all this follows. X is an element of this, so x is an element of that, and then f of x is an element of that. Yes. Boom. See you later, bud. The parenthetical reminder, x is an element of A present in both versions of the definition is included to ensure that x blee 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 blee. I'm just seeing how much left we got in here. Hey, this isn't so bad. Oh no. Okay, where were we at? Here. The parenthetical reminder, x is an element of A, present in both versions of the definition, is included to ensure that x is an allowable input for the function in question. When no confusion is likely, we may omit this reminder with the understanding that the appearance of f of x carries with it the implicit assumption that x is in the domain of f. On a related note, there is no reason to discuss functional limits at isolated points of the domain. There's no reason to discuss functional limits at isolated points of the domain. Thus, functional limits will only be considered as x tends toward a limit point of the function's domain. Why is that? There's no reason to discuss functional limits at isolated points of the domain. Okay, that makes sense. Yep, that's actually pretty straightforward. Okay, to familiarize ourselves with definition 4.2.1, let's prove that if f of x is equal to 3x plus 1, then the limit as x approaches 2 of f of x is equal to 7. okay, so usually if I were to see this, then I would just be like, limit as x approaches 2 of f of x, where f of x is equal to 3x plus 1. Then I would just plug in 2, and then that equals 7. But let's see how we're mathematically supposed to prove this. So you let epsilon be greater than 0. So then you say that there exists a delta greater than 0 such that x minus what it goes to, which is 2, is less than delta. Then you'll have that f of x minus 2. No, the limit point, L. Yeah, because as x approaches 2 as x approaches 2 over here, it'll approach 7 over here, which is L, and that's C. Yeah, dude, I don't even have to touch the keyboard, man. Such that this is true. And for this to be true, then you'll need, notice that, okay, so this, okay, so then we plug in what f of x is. So we say 3x plus 1 minus 7 is less than epsilon, right? And then this is just going to be 3x minus 6 is less than epsilon, which is then just going to be x minus 3 with a 3 factored out, less than epsilon, so then epsilon over 3. So you have to choose a delta, which is less than, which is epsilon over 3, yeah. Is that right? Yeah, 3 times x minus, whoops, it's 2. It's 2, bro. Brother, it's 2. Yes, because 3 times 2 is 6. Get your factoring right. I'm a little too advanced to be focused on how factoring works correctly, okay? I'm a little too advanced for that, so not my fault, actually. Okay, so why is this? Let's get the eraser out. Oh my god. Let's just erase all of this. So why does this now? Because x minus 2 being less than delta, where delta equals epsilon over 3, right? Then we'll have f of x minus 7 is less than epsilon. So then epsilon is equal to 3 delta. Okay. Which is going to be 3x plus 1 minus 7 less than 3 delta, right? Which now we've concluded that this is x minus 2 times 3, which is less than 3 delta, which is then just going to be x minus 2 is less than delta. 3, which is going to be 3 times epsilon over 3, which is now equal to epsilon. So when you have that, oh, okay, I've never actually walked through it that explicitly. But yeah, I guess that makes sense. Yeah, if you choose delta equals epsilon over 3, then suddenly this will now add up. Right? You'll have 3x plus 1 minus 7 is less than 3 delta. Yeah, okay. Okay, let's do that. Let's do that from scratch, and let's not even look at this, right? So you got limit as x approaches 2 of f of x equals 7. And we're trying to prove this. So we want this such that this is true. And in order for this to be true, then let's just plug in what f of x is. So it's 3x plus 2 plus 6. Pretty sure. No, it's 3x plus 1 minus 7. That's what it was. Is less than epsilon, and so we'll get 3 and then x minus 2. Right? which is less than epsilon. So then x minus 2 is now less than epsilon over 3. So you can see this x minus 2 and this x minus 2 over here. This statement is only true if delta is equal to epsilon over 3. So then therefore we'll have x minus 2 is less than delta, which is now equal to epsilon over 3. Yeah, wait, yeah, so this is true. Wait, what the hell? What? I can only undo a limited amount of times? What the hell? Okay. I wish you could right-click to erase. Why don't they have that option, dude? That's so stupid. But yeah, delta is equal to 3, so then epsilon would be equal to delta 3, or 3 delta, I guess. How the mathematicians like to do it. Yeah, and so then in that case, then you'd have x minus 2 is less than epsilon, which is equal to 3 delta, which is equal to 3 epsilon over 3. So then it's less than epsilon. So you get back what you want. Yeah. Okay. I guess it just makes sense. It's kind of like the thing that surprised me is like how are we able to get from like this very specific thing to like this form? But like that's just because it's true. But it's cool. This abstract definition kind of lines up with something that's like so intuitively, obviously, going to be true. Okay, let's show that the limit as x approaches 2 of g of x is equal to 4, where g of x is equal to x squared. Okay, let me try to do this myself. So limit as x approaches 2 of g of x equals 4, where g of x is equal to x squared. So in this case, we have x minus 2 has to be less than a delta, such that we get g of x minus 4 is less than epsilon. So this is only true when, let's plug in, so x squared minus 4 is less than epsilon. Fuck, I think it's x minus 2, x plus 2, right? And then we can drag that over. So we have x minus 2 less than epsilon over x plus 2. Can we do that? Can we do that? The presence of the variable x causes some initial confusion, but keep in mind that we are discussing the limit as x approaches 2. If we agree that our delta neighborhood around c equals 2 must have a radius no bigger than delta equals 1, then we get the upper bound, that x plus 2 must be limited to 3. Okay, so what we're requiring is that, so this c, which in this case is equal to 2, we're saying that we want this delta neighborhood to have a radius no less than 1. And so in order for that to be true, then we need x plus 2 to be bounded by 3, x to be bounded by 3. Because x approaches 2, so an x has to have this upper limit of 3. So then we can say epsilon over x plus 2 is then just going to be bounded by epsilon over 3 plus 2, which is equal to epsilon over 5, which is going to be what we want our delta to be. I'm hearing like ever so slight static in these She's just weird. It's kind of just annoying, but it's probably have to do with the connector. Okay. So we have our delta equals to this, but we also will want our delta to actuals. So we want our delta to be equal to the minimum of 1 and epsilon over 5. I guess. Why does that make sense? Hello, ChatGPT. Why? Oops, unable to upload that screenshot. Wow, that's just freaking amazing. That's incredible. That's incredible. It's incredible. It's the most incredible thing we've ever seen, folks. Folks, it's so incredible. Oh, the screenshot would not upload into ChatGPT. Okay, ChatGPT would not allow the screenshot to upload. I don't know why. Why do we choose a delta such that it is the minimum of 1 epsilon over I'm like not even kidding, but I feel like there's like static building up in my freaking ears, man. Why is that? Does it happen with these? No, these feel better. Is it because the MacBook is... I mean, I know it gives high impedance. Is it because the impedance is too high that it's outputting to these earbuds? I don't know. It's kind of giving like a weird sound. You know what? We're just going to not use the earbuds then. It's kind of giving like a weird vibe in my ears. I think it's also just because I have this at such a low volume. No, the staticky thing's still there. I don't know, it's just the laptop that's doing that. I don't know. Maybe something's wrong with the laptop? I have... I can also... Hello? Okay, well... Yeah, I know you can hear that. Huh. This, I believe, is just giving me the raw output, though. Can you hear me when I talk like this? No? I don't know. Okay. Well, guys, we're actually gonna use the mic. We are gonna use the more calibrated mic, so now it's gonna sound better. Okay, it's gonna sound a lot better for you. I just don't like the pop filter. It's just like blocking my face. Like my face is like hiding behind the pop filter. I don't really like that. I can just put it, yeah, I can just put the mic a little bit further away, I guess. But then at that point, there's no use for a pop filter. Like, it doesn't really do anything at that point. But, I don't know. Still just, cramp in my palm, dude. What the hell? I'll still just, yeah, I'll keep it there, because it's at a far enough distance. I'll turn that down a little bit. Okay. Alright, guys. Okay, why does it do that? Why does it do that? I know why epsilon over 5. Oh, because you also want to satisfy x plus 2. Okay. Yeah, okay. That would make sense, because you have this conditional, this other conditional bound, and so you want to meet both of these, well, I guess you want to meet both of these bounds, right? And in order to meet both of these bounds, you're going to need to do the minimum of that. And then, yeah, then it would follow that x squared minus 4 is equal to x blah, 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 which is less than delta. So epsilon is then equal to 5 delta. So you have 5 delta, which is going to be 5 epsilon over 5, which is just going to be less than epsilon. And the limit is proved. Wow, guys. I guess those are elegant proofs, but they're also just kind of dumb proofs, okay? They're kind of stupid. They're kind of stupid. These are the stupidest proofs I've ever seen. Okay, people. Okay, people. We're looking at this, and they're saying that these are proofs for functional limits. I've never heard of them. Functional limits. What are those? I said, what are those? But apparently, they're the best. They're the greatest thing that this country has ever made. So I told them, okay, don't teach me, I don't need to understand the functional limits, but teach it to the children. To the fellow American children, teach them functional limits, so that they can calculate the var, delta, the delta and epsilon neighborhoods to make their functions continuous. Okay? Let them define what a continuous function is. I guess it technically doesn't actually define what continuous is, it just defines the limit. Because continuity is that it attains the value at all. There's no disconnection at any points. But with a functional limit, there can be a disconnection at the point itself. We're only concerned with the limit approaching. So we're dealing with epsilon and delta neighborhoods, so it's not necessarily true that it's continuous, I don't think. Otherwise, they would have mentioned it, okay? Okay, where was I? What the hell? Okay. Sequential criterion. Brother, wrap it up, guys. Now this is getting boring. Wrap it up, guys. What do I have to do tomorrow? Yeah, I'm already thinking about how I'm not gonna finish this. But it's true. I mean, like, we've been live for what, an hour now? So. I was about to do the Trump voice again, but I won't. There are people blowing up my phone, okay? I'm sorry, I'm just that popular. I'm just that popular. You thought I wasn't gonna do it, but I'm gonna do it. I'm trying to improve my Trump impression. But I fear it's just getting worse as time goes on. Sequential criterion for functional limits. We worked very hard in Chapter 2 to derive an impressive list of properties enjoyed by sequential limits, in particular the algebraic limit theorem and the order limit theorem proved invaluable in a large number of arguments that followed. Not surprisingly, we are going to the analogous statements for functional limits. Although it is not difficult to generate independent proofs of these statements, all of them will follow quite naturally from their sequential analogs once we derive the sequential criterion for functional limits motivated in the opening discussion of this chapter. Okay, I need to stop. I'm sorry. Okay. Theorem 4.2.3, sequential criterion for functional limits. Given a function f a to r and a limit point c of a, the following two statements are equivalent. The limit as x approaches c of f of x equals L, sure. For all sequences xn that are subsets of A, satisfying xn is not equal to C, and xn converges or approaches C, it follows that f of xn goes to L. So we have A here, right? We have A and we have some sequence xn, which approaches some point C. So then we're saying that it follows that f of xn approaches L. That f of xn approaches L. I guess I'm trying to understand this before reading the proof, but I feel like the proof wouldn't help. I'm trying to get a geometric picture of it, which I think is the strongest. Some point C. And then you're saying you have some sequence. Oh, so you're saying the limit of a function as it approaches C is going to be equal to L. And if a sequence converges to C, so we're saying if xn is going to converge to C, then we're going to say that f of xn converges to f of C, which is equal to L. Okay, sure. Listen, guys, I'm pretty busy, okay? I'm pretty popular and busy. I'm not... Why do I have this? Where did this come from? Why do I have just a blank index card? Oh yeah, for what I have to do tomorrow. That's why I have a blank index card. April 10th, 2024. I should start... Actually, is it due tomorrow? Is my math homework due tomorrow? No, it's not. It's due on Thursday. So I should start 104 homework. I should probably just finish it, honestly, that same day. Finish reading 104, the book, and then start reading 141A, chapter 15. I presume we're going to be moving on to chapter 15. I have to go to the gym in the morning, do cardio and wrists and shoulders. Really want to emphasize doing the wrist routine. Then I don't know. You got to get 10K steps as well. Did I hit that today, actually? Did I hit 10K steps today? I did not. Shit. Oh my god, I gotta take a lot of steps, don't I? Boy, oh boy. How did I hit 10K steps the other day? What am I gonna do to hit these steps, man? Just walk around campus? I guess I could do that at night. Oh, I gotta hit these steps, man. God damn. That's annoying. What can I do while trying to get the steps? I don't know, I could listen to something? Listen to a podcast, maybe? Yeah, I can listen to a podcast, I guess. Damn. That's annoying. Oh well, play the cards that I'm given. Oh well, play the cards that I'm given. Okay. Yeah, because that's one of my goals. Might be able to knock out talking with a stranger today as well. Who knows? Who knows? I told the witch doctor, gotta knock with you, bum 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 bum. You guys remember that classic? That classic? Okay. Back to this. Let's look at the actual formal proof. Okay, because the formal proof is pretty important. So, formal proof of this. What's going on? For all sequences xn, which is a subset of A satisfying xn is not equal C, and xn approaches C, it follows that f of xn goes to L. So let's prove this. Let's first assume that the limit of x approaches C of f of x equals L. To prove 2, we consider an arbitrary sequence xn, so we're assuming this is true, right? So then we just take, let's say there exists some xn that converges to C, where xn does not equal C, right? This is our little stipulation. Our goal is to show that the image sequence f of xn converges to L. This is most easily seen using the topological formulation of the definition. So we let epsilon So say, whoops, epsilon is greater than 0. So then there will exist a delta neighborhood of C such that X is an element of this delta neighborhood of C. So because we're assuming this implies that there exists a delta neighborhood of C with the property that all X is an element of this delta neighborhood, different from C, and those X's satisfy that their image is a part of some epsilon neighborhood of L. Yeah, which will imply that f of X is a part of an epsilon neighborhood of L. This is pretty clear if we draw this graphically. What's going on, right, is that we have some point C here, or this is X, this is f of X, and then we have our function here, and then we're saying that at this point C, in the image space output, there's some region here, some delta region, there's some epsilon region here, where f of X is a part of this region right here, which is pretty clear from this picture. So all we need to do then is argue that our particular sequence xn is eventually in this. Well, that makes sense because we're stipulating that xn converges to a point in C. So of course our xn is going to appear in here. But we are assuming, yeah, that xn approaches C. So this implies that there exists a point xn after which xn, okay, so we're saying that there exists some xn such that xn, small n, is an element of this neighborhood. Because we're saying that this sequence converges to C, so we're going to say after some point, you know, n could be anything. This big N, where big N is going to be greater than or equal to n, right? We're saying that in later parts, it'll converge to some point in here because it has to converge to C. So some xn, some specified xn, will be in this neighborhood of that. Oh, n greater than or equal to n. Oh, because we're, yeah. Okay, remember when I was saying this, that since this, then xn should be an element of this, there was a disconnect. If I did xn and then x capital N, then this would be true. But this is now true. Because we're looking at some xn, right? We're looking at some sequence where this is, you know, say this is our sequence where this is our nth thing. Then we're looking at all the following n ones, which are in this epsilon neighborhood of C. Oh no, I can only erase so much. Okay, so we'll just scribble it out. Okay. So then this will imply that f of xn is in our epsilon neighborhood of C. Well, not of C, of L, as desired. Yes. Okay, now to go the other way. So this has all been proving this way, right? That way. Now if we want to go the other way, what do we have to do? To go the other way, guys, let me remind you what we have to do. I'm going to read. So to go the other way in the proof, what do we have to do? We give a contrapositive proof, which is essentially a proof by contradiction. Thus, we assume that the statement 2 is true and carefully negate statement 1 to say that the limit does not equal L. To say that this limit does not equal L means that there exists at least, okay, so we're going to do a proof by contradiction. So we're going to say that the limit as x approaches C of f of x does not equal L. So this is, we're going to say is not true, right? For this to happen, then we have to do the opposite of what we assume. So instead of for all epsilon greater than 0, there exists a delta, we have to negate this. So we have to go, there exists some epsilon greater than 0 for which all delta for all epsilon there exists a delta. So there exists an epsilon for all delta. Okay, I'm kind of for no deltas. There's a way to write this properly, but just going by the textbook, we're gonna say, okay, there exists an epsilon for which such that no delta is right. So in other words, no matter what delta greater than 0 we try, there will always be at least 1 point. So there will always be, so for all delta greater than 0, it follows that there is always at least 1 point x, which is in this neighborhood, where x is not equal c, for which f of x is not an element of this neighborhood. Okay, yeah, that makes sense. So we're assuming that some epsilon naught exists such that no delta is a good choice, which in other words is saying that if we have some c, we have some neighborhood here, right? Then we're saying that this f of x right here, because this is x, this is f of x, we're saying that some f of x point here is not in this epsilon naught neighborhood. We're saying that this L is not here. But now notice that the result of this is a sequence xn approaching C, where the image sequence f of xn certainly does not converge to L. Because this contradicts 2, we are assuming this is true for this argument. Ah, okay. Oh, I see what they're saying. So they're basically saying, like, if we're doing this for some C, so if we assume, that xn is going to approach C and that f of xn is going to approach L, right? But then, if we then take this assumption and then we kind of try to negate what 1 is saying, then we end up with this weird world where somehow we can have a sequence that converges at this point in this neighborhood and have the image of that sequence be in some epsilon neighborhood, but have a point itself in this epsilon neighborhood somehow not be in this neighborhood, which is then that can't happen. You can't have the sequence, you can't have a sequence around this neighborhood converting to some neighborhood, epsilon neighborhood there, and but not have the point converting to that point, you know? Like, you can even just see it in this picture. Like, there's no way to picture it because it doesn't make sense. Boom. We're killing it, guys. We're killing it. So, now what? So theorem 4.2.3 has useful corollaries. In addition to the previously advertised benefit of granting us some short proofs of statements about how functional limits interact with algebraic combinations of functions, we also get an economical way of establishing that certain limits do not exist. Okay. Corollary of 4.2.4, the algebraic limit theorem for functional limits. Let f and g be functions defined on a domain A, which is a subset of the real numbers, and assume that the limit of x approaching c of f of x equals L, and the limit of x approaching c of g of x equals M for some limit point c of A. Then, the limit as x approaches c of k of f of x is going to be equal to k times L. The limit as x approaches c of f of x plus g of x is going to be equal to their the summation of their limit points. The limit as x approaches c of f of x times g of x is going to be equal to the product of their limit points. And the limit as x approaches c of f of x divided by g of x is going to be equal to the division of their limit points, provided that m is not equal to 0. So the proof for these follow from theorem 4.2.3 and the algebraic limit theorem for sequences. The details are requested in exercise 4.2.1. I guess this kind of makes sense. Let's try to see. So for all sequences, so we're saying limit of f of x equals L. So we can just do limit as x approaches c of k of f of x is going to be equal to k times the limit as x approaches c of f of x, which is going to be equal to L. Like, can we just do that? Or I guess we can't. Is that not how you can't really prove it like that? I guess you have to use like a var epsilon neighborhood argument. Probably. Yeah, you probably have to use like an epsilon neighborhood argument because there's like, you can't just pull things out in a proof, surely. I don't know. We're not gonna go over this. I'm like, I feel like this is like a homework assignment, right? 4.2.1. Oh, this is not a homework assignment. Okay. I think we proved it in class then? Hold on. Let me go to my notes. Let me go to my notes real quick, guys. Stay tuned. You might learn a little something. So if I'm going to check my lecture notes, and this is on functional limits, that was before spring break, so obviously we did not cover it then. We really cover a lot. Oh, we went to extreme value theorem somehow here. How did we do that already? Oh, we already did continuous functions? Wait, this cannot be true. What the hell? Did I click on the wrong thing? I think I clicked on the wrong thing. Yes, I did. No, I didn't. I must have missed that class. I don't know. But anyway. Let's just keep reading. Our job is to not solve this. We're taking this for a given, okay? It's not a homework assignment, and it's also not something that we have to prove. So we're going to take it as a given, all right? So we're going to move on to corollary 4.2.5, divergence criterion for functional limits. Let f be a function defined on A, and let c be a limit point of A. So f is a function defined on A, c is a limit point of A. If there exists two sequences xn and yn in A, with xn not equal to c and yn not equal to c, and the limit of xn being equal to the limit of yn equals c, but the limit of f of xn not being equal to the limit of f of yn, then we can conclude that the functional limit x approaching c of f of x does not exist. This makes sense. Let's visually look at what we're talking about. So we're saying the limit of x of xn equals c. We're saying the limit of yn equals c. So then the f of xn should be equal to f of c, and f of yn should be equal to f of c. But if the limit does not equal to the limit of that, then what's happening pretty much is that there's some sort of discontinuity, is how you can view it. So we're saying that at C, we're saying that both of these subsequences exist in this plane. So both xn can approach, like the sequence xn can come to C, and the sequence yn can come to C, but we're saying that f of xn, so let's say this is, or we're just saying that the limit of f of xn does not equal to the limit of f of yn, and that's because the limit basically talks about going for both sides, right? This should be a valid reason why. I think there's probably some example that you can come up with though, where it's not necessarily when you write it down. There's probably an example of this where you're not gonna have like this big discontinuity. Like there's probably an example of a continuous function where you can find two sequences that like their image does not whatever to the same whatever. But I'm not gonna think about that because that's not my job. It's not my job to think about things in that way. My job is to read. So, example 4.2.6, assuming the familiar properties of the sine function, let's show that the limit of x approaches 0, sine of 1 over x does not exist. Okay, so we're saying if xn equals 1 over 2n pi and yn equals 1 over 2n pi plus pi over 2, so phase shift a little bit, then the limit of xn equals the limit of yn, which is equal to 0. Yes. Well, the limit is what? Limit of xn? Like, what is this? Is x approaches infinity? Like, n approaches infinity? Like, what's the limit? What's the actual limit? As x approaches 0, I guess? I'm confused. I'm confused on how you take these limits. Well, ChatGPT time. Let's ask. Why does the limit xn equal 0? Let's just say that, because if we say limit xn equals limit of yn equals 0, it might be like, well, you know, like yn and they both approach 0, but I'm asking why does it approach 0? That's the important question. But let's keep reading. However, sine of 1 over xn equals 0 for all n, it's an element of the natural numbers, while sine of 1 over yn equals 1. Let's see. So we're saying sine of 1 over 2n pi equals 0, but sine of 1 over 2n pi plus pi over 2 equals 1. This would kind of make sense because plussing by pi over 2 is effectively what it's doing is it's taking our sine function, and if we're plussing by pi over 2, I think we're moving it either to the right or to the left. I forget. I think to the left, where like you're phase shifting it by pi over 2. So now our new thing is starting at pi over 2, like something like that. It's a crude picture. It's a crude approximation. Okay, you get what I mean. Yeah, it's as n approaches infinity. Okay, so I guess it's just implied. But yeah, that would make sense. As n approaches infinity, these things grow. And then I guess there's no way to like, you just have to calculate this. But sure, I'll trust their calculations on this one, but okay. So by corollary, 4.2.5, the limit as x approaches 0 of sine of 1 over x does not exist. And you can actually see that. It's like all fucked up. Okay, now we're on to continuous functions. How long is this chapter? Actually not too long. It's only like 4 pages actually. So we can probably do this. It's only 4 pages. It's only 4 pages. Haven't you heard? It's only 4 pages. Can you believe that? I can't believe that. But okay. Continuous functions. Wow, no way. So everything up until this point, it's building up. And what it's building up to is describing continuity in functions, because we've already described continuity somewhere here, man. I swear to God, we've described continuity somewhere else. Wait, no. I don't know. Okay, whatever. We now come to a significant milestone in our progress towards a rigorous theory of real-valued functions, a proper definition of the seminal concept of continuity that avoids any intuitive appeals to unbroken curves or functions without jumps or holes. Definition 4.3.1, continuity. A function f that goes from a to r is continuous at a point c, which is inside of a, if, for all epsilon greater than 0, there exists a delta greater than 0, such that whenever x minus c is less than delta, and x is an element of a, it follows that f of x minus f of c is less than epsilon. Oh, so that's the assumption I was baking in earlier, where I was saying f of x minus, where previously I was like f of x minus f of c, rather, like it was supposed to be c. I was like, oh, it's f of c. But no, that's my assumption earlier. Is less than epsilon. So if f is continuous, oh, that's because previously it was, previously all of these arguments were dependent on a specific point, L. Like L is some specific defined point. So we could only really talk about, we were just talking about it at a specific point, L. But now what we're saying is that on any given c, then any f of c is going to be within that delta, that epsilon neighborhood. So now we're generalizing it, and we're saying that that means it's continuous, because this is the definition of a limit. If f is continuous at every point in the domain A, then we say that f is continuous on A. The definition of continuity looks much like the definition for functional limits, with a few subtle differences. The most important is that we require a point C to be in the domain of f. The value f of c then becomes the value of x approaching c of f of x. With this observation in mind, it is tempting to shorten definition 4.3.1 to say that f is continuous at c if limit as x approaches c of f of x is equal to f of c. This is fine as long as c is a limit point of a. If c is an isolated point of a, then the limit as x approaches c of f of x isn't defined. Yes, because it's an isolated point. We can't talk about limits approaching anything if it's just one single point. But definition 4.3.1 can still be applied. An unremarkable but noteworthy consequence of this definition is that functions are continuous at isolated points of their domains. Functions are continuous at isolated points of their domains. Oh. So we're saying that this is continuous. That some function f of x on this point is still considered continuous. Okay. That would make sense too, because later, spoiler alert, I learned this today in class, but this function can be continuous, but like at this single point, but it can't, but its derivative does not exist at some point C. I don't even know why I brought that up. That's not even related to what we're doing right now, but I hate that you can only do like a certain amount of undos. It's annoying. But anyway, we saw in the previous section that in addition to the standard epsilon delta definition, functional limits have a useful formulation in terms of sequences. The same is true of continuity. So functional limits have a useful formulation in terms of sequences, and the same is true of continuity. The next theorem summarizes these various equivalent ways to characterize the continuity of a function at a given point. Theorem 4.3.2, characterizations of continuity. Let f be an element, let f map A to R, and let C be an element of A. The function f is continuous at C if and only if any one of the following three conditions is met. For all epsilon greater than 0, there exists a delta greater than 0 such that x minus c is less than delta, implies f of x minus f of c is less than epsilon. For all var epsilon neighborhood of f of c, there exists a delta neighborhood of C. Where did I come with that var? Did I just come up with that, or did I hear my professor say that? Maybe I came up with it. No, maybe I heard my professor. I don't know. Anyway, for all epsilon neighborhood f of C, there exists a delta neighborhood V of C, delta neighborhood of C with the property that X is an element of this delta neighborhood of C and X is an element of A, which implies that f of X is, yeah, okay. So these are all basically describing this little picture that you have C, you have some delta neighborhood, you have something like this, you have this, and it's mapping on to, this is f of C, and it's within some epsilon neighborhood, right? It's not C. I guess we'll just say f of C. If xn approaches C, okay, so the first thing we were saying is that this delta neighborhood, we were just writing it down like in words, this delta neighborhood, if x minus C is less than this delta neighborhood, then f of x minus f of C is going to be less than this epsilon neighborhood. The second one is just, hammering home that point. And the third one is equivalent because it's saying if xn, so we're saying if some sequence converges to C in this point, then f of xn will converge to f of C. So we're taking the function, so we're taking the image of that sequence, and it will map on to some f of C. Because we're saying that if this sequence is converging to C, then the function of that sequence will converge to f of C. If C is a limit point of A, then the above conditions are equivalent to the limit as x approaching C of f of x is equal to f of C. Wow. I need to pee real quick. So ponder on that in the meantime while I pee. Think about that. Think about that picture. Think about how cool it is. It's not cool, but my name is Turkey Tom, and until next time, leave me alone. Okay. We're back. Hope you pondered on that question, okay? Let's go through the proof. Statement 1 is just definition 4.3.1, and statement 2 is a standard rewording of 1 using topological... Oh my god, would you look at that? Using topological neighborhoods in place of the absolute value notion. Statement 3 is equivalent to 1 via an argument nearly identical to that of 4.2.3, with some slight modifications for when xn equals C. Finally, statement 4 is seen to be equivalent to 1 by considering definition 4.2.1 and observing the case x equals C, which is excluded in the definition of functional limits, leads to the requirement f of C is in that neighborhood, which is trivially true. Yes. So the length of this list is somewhat deceiving. What? Statements 1, 2, and 4 are closely related and essentially remind us that functional limits have an epsilon delta formulation, as well as a topological description. Statement 3, however, is qualitatively different from the others. As a general rule, the sequential characterization of continuity is typically the most useful for demonstrating that a function is not continuous at some point. The sequential characterization of continuity is typically the most useful for demonstrating that a function is not continuous at some point. Okay, sure. Corollary 4.3.3, criterion for discontinuity. Let f map from A to R, and let C be an element of A, be a limit point of A. If there exists a sequence xn, which is in this thing of A, where xn converges to C, but such that f of xn does not converge to f of C, we may conclude that f is not continuous at C. Yes, and that has to do with the picture I was drawing before, where we had some C, right? And then let's say we have like f of C is here. And it's not converging to that point. I don't know. I don't know if that picture is accurate actually. I don't know if I can draw a picture for that. That's kind of, I don't know if I can I? Yeah, I don't know if I can really draw a picture, but it makes sense if you're just writing it down. I guess there's no proof of it, but it just makes sense. The sequential characterization of continuity is also important. Bruh. Oh, that might be why. The sequential characterization of continuity is also important for the other reasons that it was important for functional limits. In particular, it allows us to bring our catalog of results about the behavior of sequences to bear on the study of continuous functions. The next theorem should be compared to corollary 4.2.3, algebraic continuity theorem. K f of x, so assume f maps and g are continuous, then k f of x is continuous, their addition is continuous, their multiplication is continuous, and their division is continuous. Sure, that makes sense. Yeah, all these statements can quickly be derived from corollary 4.2.4 and theorem 4.3.2, which is this one. So these results provide us, why can't math textbooks just like write out the proof, man? Why do they have to do this whole, it's pretty obvious that it can be derived when it's not that obvious. Like it's not trivially obvious. But anyway, these results provide us with the tools that we need to firm up our arguments in the opening section of this chapter about the behavior of Dirichlet's functions and Thomae's functions. The details are requested in exercise 4.3.7. Here are some more examples of arguments for and against continuity of some familiar functions. So all polynomials are continuous on R. In fact, rational functions, i.e. quotients of all polynomials, are continuous wherever they are defined. To see why this is so, consider the identity function g of x is equal to x. So g of x equals x. Because g of x minus g of c is equal to x, undo some of that, this is equal to x minus c. Yep. We can respond to a given epsilon greater than, so it's less than delta, less than epsilon. So choose delta equals to epsilon, and it follows that g is continuous. Yeah, I guess, yeah, because then it just, yeah, it just meets the definitions of continuity. Which is this in particular, this one, yeah. Okay. It is even simpler to show that a constant function f of x equals k is continuous. Letting delta equal 1 regardless of the value of epsilon does the trick, I guess. Because an arbitrary polynomial p of x consists of sums and products of g of x with different constant functions, we may conclude from theorem 4.3.4 that p of x is continuous. Theorem 4.3.4 is this. Yeah, because the polynomial, yeah, they're just g of x, but with different constant functions. They're sums and products of g of x. So then that also necessarily will be continuous. Likewise, theorem 4.3.4 implies that quotients of polynomials are continuous as long as the denominator is not 0. Yes. In example 4.2.6, we saw that oscillations of sine 1 over x are so rapid near the origin that the limit as x approaches 0 of sine of 1 over x does not exist. Now consider the function g of x. So now we're considering the function g of x, which is equal to x sine 1 over x if x is not equal to 0, and then 0 if x equals 0. To investigate continuity of g at c equals 0, we can estimate, okay? So we want to c equals 0, so then g of x minus g of c is going to be equal to x sine 1 over x minus 0. X sine 1 over x, which we're putting a boundary on it as being less than x. So then given some epsilon greater than 0, then we'll have x is less than delta. So then g of x minus g of 0 less than epsilon is just going to be equal to, yeah, so then that's just going to follow. Thus g is continuous at the origin. This is kind of stupid though. A little stupid, but okay. Sure. Example 4. See, those examples are like ones that like they seem so circular. It's like what the hell? Why? But okay. 2 more pages and then we're done. Throughout the exercises, we have been using the greatest integer function, h of x equals that, which for each x element of R returns the highest integer n. This familiar step function certainly has discontinuous jumps, but it is a useful exercise to try and articulate this observation in the language of analysis. Given an m, which is an integer, define the sequence xn by xn equals m minus 1 over n. So we're given some m. So we're going to define xn being defined as okay, so then xn approaches m, but h of xn approaches m minus 1. Given epsilon greater than 0. So now let's see why h is continuous at a point c, which is not an element of z. Or not an element of integers. Not an integer. Given epsilon greater than 0. So epsilon greater than 0, we must find a delta neighborhood such that, so we need to find a delta neighborhood of c such that x is an element of this neighborhood. which would imply that h of x is then an element of the epsilon neighborhood of h of c. Okay, yeah, because we're treating this just like a function. Where previously, remember, we have our x is over here, and then some h of x, and then yeah, we're just saying that this oh, this isn't x, this is c, this is x, that's h of x. And so we're saying within some delta neighborhood, there's some h of x, which exists in an epsilon neighborhood. So we know that c falls between consecutive integers n, c, and n plus 1 for some n, which is an integer. If we take delta to be the minimum of c minus n, n plus 1 minus c, the minimum of are we just subtracting c from both sides? I don't know. I don't know what's going on. And then it would follow, well, it kind of just follows intuitively that h of x equals h of c. But I guess, yeah, you have to choose a proper delta. Just the choice of that delta I'm not quite understanding, but that's okay. It's okay. For all x, which is an element of this delta neighborhood of c, thus we certainly have that h of x is an element of the epsilon neighborhood of h of c. That's kind of just, clear from this picture. We said that h of c is here, but if the requirement for h of c to be able to be here is that we choose some proper delta, so that this delta projection neighborhood, this isn't a perfect picture, but so that the delta projection neighborhood is encapsulated within the epsilon neighborhood, blah 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 blah, blah 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 blah. This latter proof is quite different from the typical situation in that the value of delta does not actually depend on the choice of epsilon. Usually a smaller epsilon requires a smaller delta in response, but here the same value of delta works no matter how small epsilon is chosen. Oh, I guess. Because we're just dealing with these? I don't know. I don't really quite understand this example a whole lot, but that's okay. You're not gonna win them all, you know? You know, folks, you're not gonna win them all. You know? You win some and you lose some. That's what I always said. Okay. Oh. Okay, we got two more. We got one more example and one more theorem, and then we're done. For now, because I've been doing this for 2 hours now. And I'm reaching my limit point. It's 6:35, as you can see up here. Oh, now you can see the date and everything like that. That's kind of cool. Okay. I don't know what's worth fighting for. Hold on. Is that what's keeping up my computer? Bruh. I think what's keeping up my computer is just some stupid page. Have they implanted? Sorry, I'm seeing like I'm seeing something's taking up most of my screen time, and it's like it's a website. Not like a suspicious website, but like a website at my school. And it's just, I don't know, that's just weird. Anyways. Example 4.3.8. Our last example. Consider f of x equal to the square root of x, defined on A. Exercise 2.3.1 outlines the sequential proof that f is continuous on A. Here we're gonna give an epsilon delta proof of the same fact. Let epsilon be greater than 0. So we need to argue that f of x minus f of c can be made less than epsilon for all values of x for all x that are in some delta neighborhood around c. Oh my god, look at how I can write these mathematical statements. If you showed this to me like even a year ago and you were like, you're gonna be able to write this down and understand this, I would have been like, you're crazy. Nah, I would have been like, bet. Yeah, I know. I'm built different. All the other TikTok aphorisms, aphorisms? Aphorism? What does aphorism mean? Aphorism. A pithy observation that contains a general truth, such as, if it ain't broke, don't fix it. A concise statement of a scientific principle, typically by an ancient classical author. The opening sentence of the first aphorism of Hippocrates. Right? It's Hippocrates, right? Hippocrates. Oh. Oh. Hippocrates. Hippocrates. Okay, I thought it was Hippocrates. That's okay. Oh yeah, I guess a TikTok aphorism. Aphorism? I guess it's not really an aphorism. Saying, what did I say? I don't know. Anyways, bet. Oh yeah, that kind of thing. Yeah, bet is not an aphorism. It's not saying like a truth or something like that. It's just a saying. Ooh, I'm getting a cramp. Holy fuck. I gotta drink more water, it seems. If I finished this, I would have met my minimum requirements for drinking water in a day, which I want to be 2 liters. 64 ounce to liters, which is about... Yeah, because one of these is about 2 liters. So if I drink that, it's gonna be 4 liters. 4 liters of water. It's a good minimum. Although I should be shooting for like 8. Anyway, let epsilon blah 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 can be made less than epsilon for all values of x in some delta neighborhood around c. If c equals 0, this reduces the statement to the square root of x. Yeah, so then x minus c is less than delta. If c equals 0, then we just have x is less than delta. So then f of x minus f of c is just going to be square root of x is less than epsilon. Which implies that as long as, so x is less than epsilon squared, thus if we choose delta equals epsilon squared, we're gonna see that x minus 0 less than delta implies, yes, that this is true. For a point c different from 0, so that's for a point c equals 0, for a point c not equal to 0, we need to estimate square root of x minus square root of c. Now, guys, whenever you see this kind of thing, what should always pop into your mind? The complex conjugate, right? So we have square root of x minus square root of c, and then we multiply that by the addition of them over each other, because this is essentially, this simplifies to just 1, so we're just multiplying it by 1, which we can do, but this allows us to get x minus c over square root of x plus square root of c on the bottom. Not that, but yeah, just this. And then we can set we can just say, why can we do that? I guess we can't, yeah, this is less than or equal to. I'm not quite sure why we can just do that. Why can we do that? Let's ask ChatGPT. Let's not skip over this. This seems like something that's like pretty important. Like if I can't understand this, why do we say that x minus c over square root of x plus square root of c Asking where did the square root of x go is kind of stupid. It's kind of, no, it's not stupid. It's not really taking into consideration. What is it? Okay. Explain. Why does it hold? Explain. Also, why is the text so small on the screen? It's really small. I don't know why. Here's why the inequality holds. The denominator square root of x plus square root of c is always larger than square root of c alone, provided that x is greater than or equal to 0. This is because square root of x is always non-negative. When you divide the same number okay, so I guess we just get rid of it. Yeah, because if square root of x is a positive, is always going to be a positive quantity because square roots are only well defined for positive quantities, then, and if it's in the denominator, then if you get rid of it, it's gonna just it's gonna be a bigger thing. Okay. So now you have x minus c over square root of c is less than delta. And so x minus c is going to be less than delta square root c, right? Boom. And so you choose epsilon. Wait, what? Why am I now having like this brain moment where I'm like, wait, don't we always choose epsilon first? No, we choose what delta is so that, no, wait. Oh, wait, no. It's less than epsilon. My brain was right. This is going to be less than epsilon, because here we're still talking about we're not talking about just x minus c. We're talking about the image, which is g. So it's less than epsilon. So an x minus c is less than epsilon square root c. So we choose delta equal epsilon over epsilon square root c. Jesus, that's what, dude. My brain was like so like, wait, what? Why are we doing this? Yes, we always choose our delta based on whatever we get, like our image or output stuff to be. Yeah, because this is g of x, that's g of c. Okay. Yep, and then yup. Yes. Boom. Okay. Although we have now shown that both polynomials and the square root functions are continuous, the algebraic continuity theorem does not provide the justification needed to conclude that a function such as h of x equals this is continuous. For this, we must prove the compositions of continuous functions are continuous. Given f and g, assume that the range of f of a is equal to f of x is contained in the domain B. Okay, what is this? So we're given f, which is a to r, and we're given g, which is b to r. And we're saying that given that the range of f, so we're saying the range of f is contained in the domain B. So that the composition is defined on A, so in G composed f of x is well defined on A, yes. If f is continuous at C, which is an element of A, and if G is continuous at f of C, which is an element of B, then G composed with f is continuous at C. So if f is continuous at some point C in A, So at some point C, if f is continuous, and if g is continuous at f of c, which is a point at b, then g, so this is going to give some output. This is too confusing to graph out. It's too confusing to like visually write. I couldn't visually draw it unless I was a master at math. A master is so much doper sounding than a PhD. Like, dude, I'm a master. Like, someone asks you, like, yo, how good are you at math? And you're like, bro, I'm a master at math. Instead of being like, I have a PhD in math. You know, it just sounds so much more lame. But anyway, we're done for today. We still need to go through... In the next episode, we will go through 4.4, 4.5, 4.6... Probably skip 4.7 and move on to derivatives. But okay, that's about it. Alright guys, that's about it. See ya. Peace out.